In the last part of this lecture, we want to understand how a substance reacts to a heat flux. Okay, it's about, if you have a heat flux, how long does it take for water to warm up? How long does it take for soil to warm up? Okay, so we want to understand a little bit more about some particular features. Okay. In particular, the thermal response times. Okay, because that regulate climate, because it takes a long time to heat up the ocean. Okay. And at the same time, the ocean, because of that delay, can actually heat up the atmosphere during winter time while receiving heat in the summertime. You see, because of that interaction, we have actually much lower, much smaller seasonal temperature differences over the ocean as compared to over land. Okay, so let's don't make it too long. And I should have warned you, because here is an equation again. This equation is central to understand how a substance reacts to a surface heat flux. Okay, let's explain what this means. This is an equation. An equation means that you have an equation sign in the middle, and what's on the right side of the equation is the same compared to what's on the left side of the equation. That's what the equal means. It is a balance. And these type of equations, it has an additional meaning. It means whatever you have on the right-hand side is the cause of something that happens on the left side of this equation. So let's have a look at it. What's written on the left-hand side is the temperature of a material, okay, that has a square meter surface and has a depth that we call H, shown here. So this is what we're talking about. The temperature of a block of material. It can be ocean, can be seawater, or it can be soil. We're looking at surfaces on Earth. Okay? So, in the temperature, what's written here is dt, the change of the capital T, which is temperature, and this lowercase t is time. So what it means here is the change with time. Okay? Is a consequence of what's written on the right-hand side. And here you can see the heat flux, the surface heat flux. Okay? If it is positive, the surface heat flux, the left side is positive, which means that the temperature will increase. All the other terms here are positive quantities. If the Q net is negative, causes a temperature decrease. So the sign is controlled by the Q net. Okay? All the other features here, the density, which is the mass per unit volume, the specific heat capacity, we talk about that on the next slides, and the thickness of your layer control how fast this cooling or warming is. Okay? All right. So interpretation, the sign of the heat flux determines whether a substance gets warmer or cooler. And the type of substance, the magnitude of this heat flux, and the layer thickness determine how fast temperature changes. And that's important. And that's what you want to know if you build something. You know, it's not only about about ocean and soil here. It's also about like the material you use as the roof of your house. Okay, so this equation here is a general type of equation that tells you the response in terms of temperature to a heat flux. All right. So now let us go one step further. Okay. Let us now talk about this part here of the equation, which is shown up on the right, which is the density of your substance and the specific heat capacity of your substance. Okay. So density is mass per unit volume, but what is the specific heat capacity? The specific heat capacity is the energy required to increase the temperature of 1 kilogram of your substance by 1 degree Celsius. Okay? 1 kilogram by 1 degree Kelvin. Okay, which is the same as 1 degree Celsius. If you multiply that by density, you actually get the energy required to increase the temperature of 1 cubic meter of substance per 1 Kelvin. Okay, and this is what's in here. Yeah, we're looking at a square meter times the depth or the thickness of your substance. So that's the key. Okay, and once you understand that, okay, you can look at the numbers, and this is shown here in this table. Okay, you can see the values of this product, density by times specific heat capacity, rho times this Cp, and you can look at the numbers, and you can compare seawater with air and soil. And you can see how much bigger the number for seawater is compared with air. It's 1,000 times, it's about 4,000 times larger, that number. Okay? So seawater has a much higher heat capacity compared with air, and also larger is compared with soil. Okay? Interpretation: seawater has an extremely high specific heat capacity based on a unit volume, even higher than soil. Okay? So that might be still a little bit confusing because it's not the full part of the story, because what also matters in the temperature change is actually this vertical scale, which is the thickness. So what's the typical thickness over which heat is distributed if you compare seawater and soil? Okay, so let's have a look at that second part. And this is now what we're talking about, is this vertical scale. Indeed, it's trivial. If you have a thicker layer, the heating rate will be lower. Okay, it's a trivial thing. Okay, so heat fluxes distribute heat over a certain layer thickness. In the ocean, for instance, surface heat fluxes are distributed over the surface mixed layer. And the surface mixed layer in the ocean is, if you don't, in most regions, if you just go to tropical regions or so, it's about 100 meters. Okay, you look at that. You don't worry about differences you just use 100 meters as an example. Surface mixed layer. Okay? Soil is much lower. We're talking about actually centimeters. And here we use 10 centimeters. Okay? And this is just because soil is different to the ocean. Ocean is a fluid, and you have a mechanism of mixing. The water can mix and distribute over 100 meters. And soil, you only have heat conduction. You don't have any mechanism of mixing in soil. So that's why this vertical scale is so different. We also consider the atmosphere, although it works different for the atmosphere, and you learned about that. The atmosphere is actually only heated by a sensible heat flux. It doesn't feel the entire total heat flux, but we'll just include the atmosphere and I'll just assume that it gets a same heat flux, just for comparison. Okay? And then we put the pieces together, but again, we have to do one thing more, and you will understand why that is just in a second. Now, to compare these three different substances, what we do is we look at thermal response times. What we do is we ask the question, how long does it take for the temperature of a substance to change by 1 degree Celsius? And that's how we can compare different cases. And the way to do that is to formulate the equation that we have in terms of something we call differences. Yeah, you can see these symbols here, delta T divided by delta lowercase t, is, we look at a change of temperature divided by a change of time. Okay, it actually turns into a ratio, and we can now manipulate the equation. We can put actually the time scale onto the left side of the equation and everything else onto the other side of the equation. Okay? And we know everything. Now we assume what happens if we have a heat flux of 100 watts per square meter. We plug that in, we plug in the H value, we plug in everything we know, and for the temperature change we say 1 degree. Okay? How long does it take? And we work out the time scale. This lowercase t, delta t is the time scale. So now comes our conclusion of all of that. I know it took a long time, but sometimes it's not that easy. Not everything you learn has to be written on one slide. All right, let's have a look. You have a heat flux of 100 watts per square meter, and for the ocean, for seawater to heat up by 1 degree, for a mixed layer, which is 100 meters deep, it will take 46 days, so it's 1.5 months. Okay, and that is a long time. For the atmosphere, okay, if you assume that you have a sensible heat flux of 100 watts per square meter and you mix it over the entire troposphere, the height scale is 10 kilometers, will take 1.5 days. Very, very quick. Okay. For soil, okay, it will take 30 minutes for the upper 10 centimeters. So the soil reacts very fast to a heat flux and much faster than the ocean. Okay? And this explains why you get different temperatures over land compared to over sea. Okay, because the ocean's thermal response time is relatively slow. On the other hand, you also get something we call thermal inertia, so that the ocean stays warm into the winter season and actually heats up the atmosphere. Okay, or the other way around, stays, the other way, it actually stays longer cool into the warmer seasons of the year or the summer seasons, and actually cools down the atmosphere. So there is this mechanism that the existence of water actually influences the climate on nearby land because of this thermal inertia. So I hope that this gives you something, that you learn something from these considerations. So let's just have a look at one last puzzle. Okay, no, not yet. There's something else. Come. Just showing you one example before we have a little puzzle at the end. Okay, just one example which actually shows you measurements. Okay, real measurements of looking at the top 20 centimeters of soil, showing you observations of soil temperatures at various depths, and in comparison to atmospheric temperatures observed over 1.5 kilometers. And this is in Nebraska, some long time ago, but doesn't matter what time it was. And you can see a little bit in order to understand what happens, And what you learn is that actually the soil heats up first before heating up the atmosphere through the sensible heat flux. And let's have a look at that. And shown are temperatures here. You can see the temperature range on the x-axis. On the left side is the soil temperature. And at different times, it starts 6 o'clock in the morning, then 10 o'clock, 12 o'clock, 2 o'clock in the afternoon, 6 o'clock in the evening, 10 o'clock at night. Okay? So, same time, same time of the year. And you can see that the soil actually, in due course of the day, actually gets warmer than the atmosphere. So you get 40 degrees Celsius. Okay? You can also see that only something like the upper 5, maybe 5 to 10 centimeters are actually impacted by this temperature change. Maximum temperature range at the surface. Okay, very, very thin top centimeters of the soil. Okay? This 40 degrees exceeds what you actually have in the atmosphere. Okay? The atmosphere has a response that actually heats up over the day. And there is another process that happens in the atmosphere. It actually triggers unstable density distribution. There is a lighter air over heavier air. It causes a mixing of air masses, and you can see that it actually influences the temperature of up to maybe something of 700 to 800 meters. Okay, this is the heating of that by the soil underneath influences the temperature over almost a kilometer. Okay, above that, there's nothing happening here in this. You might be surprised to see that temperature increases with height, but that's just the pressure effect that you have. Okay. All right. So this is one example of illustrating that the atmosphere is heated from the ground. Okay, and also you can see that there is a few centimeters of soil. The heat change in this layer can have a dramatic consequence on the atmosphere, the atmospheric temperature profile. All right, I think that's useful too. But as promised, a little game. Okay, a little puzzle. It's called the Find the Continents game. Okay, so here's a map, and it shows you the annular range in temperature at the Earth's surface. What is the annual range? Annual range is the maximum minus the minimum temperature. Okay? It's the summertime minus the wintertime temperatures, if you like. And you can see, and this is done for the entire globe. Let's activate the mouse, and you can see that you have latitude shown here. From north to south, you essentially go from the North Pole to the South Pole, and also all around Earth. Okay, so can you spot all continents? Where's Australia in this map? Where are the oceans? Okay. What happens near the equator? Look at here's the equator, look at there. There's a little, what are actually the maximum numbers that you can see? Maximum is, I think, 50 degrees Celsius difference over the year. Okay. Explain this distribution. And you should now be able to explain what's happening here. Okay, study questions. What is a residual heat flux? Which terms make up the residual heat flux? Which heat flux component always creates a cooling effect? What heats up faster, the surface soil layer or the surface mixed layer of the ocean? What actually drives the atmospheric dynamics? What creates winds in the atmosphere? And finally, why is the annual temperature range over land much larger than over sea? Okay, thanks for watching.